This is Shashank Singh Kumar from Georgia Tech, and this video is the presentation for my lab report on constant velocity in Physics 2211, Intro to Physics. The lab is based on the comparison of the motion of a cylinder moving in real time and a computational model for the cylinder. I will begin the lab by discussing the purpose, key ideas, and important formulas which will be used in the lab in the introduction section. I will then move on to analyzing the motion of the cylinder through the use of the tracker software, followed by a discussion of the computational model that I created on a glow script using the starter code given. I will then analyze the differences between the motion observed in real time and the motion predicted by glow script. At the end, I will answer the what if questions and what does it mean questions. The purpose of the experiment is to be able to decipher the differences between an object moving in motion at a constant velocity in reality to a model for the object based on the Python-based software glow script. The first key idea used is Newton's first law that states that an object in motion will remain in motion and an object at rest will remain at rest unless and until an external force has been applied to it. Hence, if the net force on an object is zero, the object will have a constant velocity. The following equation describes the position of an object moving at constant velocity, and this is the position update formula. The second idea used is Newton's second law, which can be represented mathematically by the following equation. This can further be used to derive the following velocity update formula. In order to set up the experiment, a cylindrical candle stand was rolled in one straight line. A video of the motion was then recorded. The video was inserted into the tracker software and analyzed. A position versus time graph was obtained and analyzed. Velocity was derived by using the formula V average is equal to delta R by delta T. The starter code was edited in accordance to the tracker software, and the graphs obtained were compared. The initial position of the cylinder in relation to the origin is 0.00956 meters. Since the velocity is assumed to be constant, we can take any 2 points on the graph and calculate the displacement between them. Then dividing that value by the time we obtain the velocity. I took the initial position and the final position in order to calculate the velocity. The velocity was found to be 4.2452352 meters per second. I used the average velocity formula in slide 4 in order to calculate the velocity. The video currently being displayed is the tracker software being used in order to analyze the video recorded. The link below will redirect you to the glow script code for my experiment. Edits made to the starter code for the initial conditions include the following. Line 37 has the coordinates for the position of the cylinder at time is equal to 0, which will represent the starting position of the ball in the code. Line 38 has the vector representing the velocity of the cylinder. The cylinder moves at a constant velocity, hence the vector will remain the same throughout the code. Edits made to the starter code for the calculation loop include the following. Line 51 has the time that the motion of the cylinder was observed in the tracker software for, hence the limits of the x-axis on the graph will be derived from this. Line 60 was edited with the velocity update formula mentioned in slide 3. Line 62 was edited with the position update formula mentioned in slide 3. The velocity update and position update formula constantly calculate the next velocity value, which doesn't change as net force is 0, and position values, which display the graphs in the next slide. The following is the result derived from the glow script code. The position versus time graph displays a straight line with a positive gradient, the y-intercept being 0.00956. This is because the cylinder does not start from the origin. The velocity versus time graph displays a horizontal straight line representing constant velocity of 4.245 meters per second. A comparison between the real-time experiments graph and the computational model's graph can be seen on the right-hand side of the slide. The real-time experiment and computational model produce very similar results due to the short span and accuracy of the experiment. However, there are discrepancies within the charts which will be discussed in further detail in the next slide. The following are errors that may have resulted in the computational model being different to the real-time experiment. The net force was assumed to be 0, and hence friction and air resistance were not accounted for. There may have been errors as some points on tracker were entered by hand, and this may have resulted in human error. The cylinder also may not have traveled in an absolutely straight line in relation to the camera, which may also have resulted in human error. This is because the cylinder was launched by hand. The first of the final questions which I will be answering is what if the axis were flipped? The magnitude of velocity would remain the same. However, since velocity is a vector, its direction would change. Hence, the cylinder, which was previously moving in a positive direction on the x-axis, would now be moving in a negative direction. Now, on to the second question. What does it mean? There are 4 forces acting on the cylinder at all times if it is assumed that it is moving in constant velocity. These include the following. Friction, force applied, gravity, and normal force. Friction will always be in opposition to the force applied, whereas the normal force will always be in opposition to the gravity. The normal force and gravity are equivalent, hence there is no motion on the y-axis. The frictional force is equivalent to the force applied, and hence there is a constant velocity in the x-axis. This is in agreement with Newton's first law. The diagram on the right helps represent these forces. Thank you very much for your time, and I hope this presentation was informative.